Okay, then this is the reminder of the definition of a normed space. You already know, right? A normed space must be first of all a vector space. Okay, over the field R, as you have studied in in linear algebra, with a map from the vector space to the non-negative real numbers, satisfying those three conditions. Then we say that, okay, the vector space X with the map is a normed space. It's a normed space. If we have a normed space, then we can define a metric space, right? So in that sense, the normed space is an example of what? That's a special case of a metric space. If you have a normed space, then what? Let's let the distance between the two elements be what? Norm of their difference. Yeah, norm of their difference. Then that distance d, the d function over here, makes a metric on that normed space X. So in other words, okay, yeah, that makes a metric space. So the normed space X with this induced metric d is a metric space then. Yeah. So the normed space is an example, special case of a metric space. Well then, let's see some different examples of the normed space here today. First of all, L sub C1R. That is the collection, set of all real variable functions which are continuous. And integrable. Integration from negative infinity to positive infinity on the whole real number line. Absolute value of f is some finite number, which doesn't have to be in general, right? Yeah. So this is the set X. This is the set X, which is the collection of all real variable, the continuous functions, which are integrable. Okay, they're improper integration on the whole real number line. Absolute value of f integrand function must be some finite number, which doesn't have to be. Right? And then that's the set X, and then let's let the map, the metric, the norm of f be just that improper integration value. And then this map is a function from x to from the vector space x to the non-negative real number. And then we can easily justify that this map satisfies all those three conditions. So then that makes what? That makes this set X is a metric space then. Okay? Sorry, normed space. Normed space. We can easily check the three conditions. First of all, if you have the zero function in this set, identically zero function in this set, then what? What must be happened to its norm value here, which is the improper integration on the whole real number line, absolute value of f of x dx, which is same as improper integration on the whole real number line, zero function, identically zero function, which must be zero, right? So if you have a zero function, then that what? That implies what? Its norm value is zero as well. Now how about the other direction? What happens if norm of the function f is equal to 0? We want to claim the function f must be identically 0 then. That's what we want to claim. Why is it correct? If the norm of the function f in the set x is equal to 0, then that must imply what? The function f itself must be identically 0 for the other direction, for the direction of the condition number 1 there. Then how do we claim that? Using contradiction method. Suppose the function f is not identically 0. Then what contradiction can you derive then? Then, of course, there exists some point x naught, okay, on the whole real number line R, at which absolute value of f value is some positive number. Then I believe it's time to use the continuity of the function f. Our function f is continuous and we have non-zero value at the point x naught, then what? Because f is continuous, there is some delta neighborhood around x naught at which what? The whole function values are positive there. But since f is continuous, especially at the point x naught we have chosen there, there is some open ball, there is some positive number delta, okay, such that the function value of f at any point x is more than half of epsilon for all point x in the delta neighborhood around x naught. That's true because f is continuous and the function value of f is non-zero. What I mean is the situation is the following. Here is the point x naught at which absolute value of the function value is positive. And then because absolute value of f, which is, actually f is continuous, absolute value is also. Because absolute value of f is continuous at the point x naught, there is some delta neighborhood, okay, around x naught, such that at every point on the delta neighborhood around x naught, their function values, the function value of values of absolute value f is what? More than half of epsilon number. Okay, half of epsilon number. So then let's let that number be half of epsilon. That's what's happening. Yeah. Where of course epsilon is some positive number. Epsilon is some positive number. Yeah. Then one must be happened to what? One must be happened to the norm of that function f we have chosen, which is same as improper integration on the whole real number line absolute value of f dx. And one must be happened to this integration, improper integration. That must be more than or equal to, I don't care what will be happened outside of that open ball around x naught. I don't care what will be happened outside of the open ball. But inside of a open ball, this is happened. The function values are what? More than half of epsilon. So the whole integration on the whole real number line must be what? At least what? At least more than or equal to what? More than or equal to delta times half of epsilon. For sure. Which is what? The area of that rectangle thing, right? Yeah. Must be more than or equal to delta times what? Half of epsilon function values. Which is definitely positive. I don't know. I don't care what delta and epsilon numbers are what. We are sure that what? This value is positive. So that means norm of f must be positive. That's a contradiction to our assumption here. We had that contradiction because what? We supposed our function f is not identically 0. Then we have its contrapositive condition, right? Then if we suppose the function f is not identically 0, then what? We derived what? Then its norm value is positive, which is a contradiction. Yeah. So we must what? Suppose, we must conclude what? The function value f of f must be identically 0 then. So we have justified the equivalence conditions of both slots here, right? So norm over f is equal to 0 is equivalently what? F must be identically 0. That was what we have claimed, which is the first condition of the normed space. The second and third conditions are more straightforward, right? How about the second condition? That's pretty much straightforward. Using what? The property of integration. How about the norm of constant multiple of the function f in this set X? That is, by the definition of the norm, that's improper integration on the whole real number line, absolute value of constant c times f of x. Which is same as improper integration of absolute value of constant c times absolute value of f function. And then by the integral property, we can take that constant outside of integration. That's what's happened. And then must be equal to what? Absolute value of the constant c times what is this integration value? This integration value is same as what? The norm of the function f itself. This is true for all function f in the set X and constant c on the real number line. So for all x, for all f in the set X and for all constant c on the real number line, norm of cf, norm of constant multiple is same as what? Constant multiple of the norm, which is exactly the second condition to be a normed space. So the second condition is easily, justified. How about the last condition, condition number 3? That's even easier. That's a kind of what? Triangle inequality thing in the metric space we have already studied in. Okay? So let's take two different functions, f and g, in this set X. Then what happens to the norm of their sum? By the definition of the norm, that's same as the improper integration on the whole real number line, absolute value of sum of two functions f and g, integrand function. Inside this thing over here is what? Real values, right? So we can immediately apply the triangle's inequality for what? Real number line thing. Yeah, by the triangle inequality, this integration is less than or equal to the integration of what? Sum of absolute values. Yeah. We can use the result of the triangle inequality for on the real number line. The inside integrand functions here are what? Real values. So that's absolute value of sum of two real numbers. So we can immediately apply the triangle inequality to this real sum. Yeah. Absolute value of sum is less than or equal to sum of absolute values. Then by the integral property, we can split the integrations. Okay, integration of the sum is same as sum of integrations. We can separate the integrations. Which is same as what? Which is same as the first integration is the norm of the first function f plus the second integration is the norm of the second function g. So for all f and g in this set X, the norm of their addition sum is less than or equal to what? Addition of each norm. That's exactly what? The condition number 3 to be a normed space. So by the 3 conditions we have checked, we conclude what? We conclude this set X with the map we have defined is a normed space. Yeah, that's what we must conclude today. If we say normed space, and then we can immediately define a metric on the same set X. So let's let the distance d between the 2 functions f and g be the norm of their difference, which is same as what? By the definition of the norm there, that is same as improper integration on the whole real number line, the difference of the 2 functions f and g integrand function. What I mean is let's let the distance d between the 2 functions f and g in that set X be this integration value, improper integration of their difference. Then the same set X, our set X, with this d function here makes a metric space. So if we have a normed space, then that automatically induces a metric space, metric norm, metric space. And that must be the d distance between 2 functions f and g in the same set. Any questions on this? That's pretty much straightforward for you. What's the definition of L sub C square at R? That is the collection of all real valued functions which are continuous and square integrable. So improper integration of the square of that absolute value of the function f is finite, which doesn't have to be in general. This improper integration may be finite or may be infinite in general, right? But if it's finite, then the function f is in this set here. That's what that means. Then what's the norm of the function f in this set? Let me erase everything else. Yeah. Now the norm of the function f in this set we want to define is, again, improper integration on the whole real number line, just this value, this finite value. Square of that function f, integrate the function f dx. Yeah, that's the definition of this norm for every element f in that set X. And then we again define the map from the set X itself to the non-negative real numbers. Then we want to claim what? this set X with this map we have just defined is a normed space. In other words, what I mean is we must check 3 conditions, 1, 2, and 3 to be a normed space there. I will leave this as assignment problem for you. That will be in the next assignment I will upload. Okay? Yeah. You can easily check the 3 different conditions for here. Then you conclude this set with the map we have defined is a normed space. Yes.
We need to take the square roots of the integral.
Oh yes, that's what I forgot. Square root, so 1/2 power. Yeah, 1/2 power. Yeah. 1/2 power must be there. Yes. So that's the 1/2 power of improper integration of square of the function f. That's the definition of that map. And then this set X with that map we have just defined makes a normed space. That's what you can check. Okay? Check the 3 conditions there. Then you can easily check it out. And then let's let the distance function d between the 2 functions f and g in this set X be what? The norm of their difference, which is same as what? By the definition of this norm, how do we rewrite it? That's 1/2 power of what? Improper integration on the whole real number line, square of the difference between f and g functions, right? Which is some finite number as well. Then the set X we have with the D metric function D we have just defined makes a metric space. So this 1/2 power of this square integration over here defines a distance between the 2 functions f and g in this set. Does it look like a distance between the 2 functions f and g practically? You know, if you have 2 functions f and g, both of which are continuous functions, defined on the whole real number line, and both are square integrable. And then what? How do you make the distance between those 2 functions practically? There are a lot of different ways to define the distance between them theoretically, not practically. And that's another way. That's one way to define the distance between the 2 functions here. 1/2 power of what? Square integral of difference. I don't know what it means geometrically here. I don't. Anyway, theoretically, that makes a metric between the 2 functions in this set. So then you can check this setting. Check that this setting is a normed space that is induces this metric. In general, how about if you have pth power in general? That's the most generalized case. Pth power, where p must be more than 1. We have proved that what? That is a normed space if p is equal to 1. That was the very first example today. And you will prove that setup over here is a normed space when p is equal to 2. How about if in general p is more than 1 and less than infinity? Yeah, p is a finite number which is more than 1 in general. Then what's the definition of L sub c power p at R? That's again a collection set of all continuous functions which are real valued, real variables, and what? P's power integrable. P's power integrable. So improper integration of P's power of absolute value of f must be finite, which it doesn't have to be in general. Yeah, this improper integral may be or may not be finite. If it's finite, then what? Yes, that function is in this set X. P is, I don't know what P is. Any finite number which is more than 1. Maybe 1.5. Whatever, which is more than 1. And then, on this set X, we define a map F. We define a map from the set X itself to, again, what? The non-negative real numbers, such that what? The map function, map value, norm of F, that will be the norm anyway. The norm of any function F is defined by one over P's power of improper integration of P's power of F on the whole real number line. Then, what is our claim? Our set X here with this map we have just defined makes a normed space. So, let's let distance function on this set, distance between the two functions f and g in this set to be what? Again, the norm of their difference, which is same as 1 over p's power of integration on the whole real number line, p's power of difference between the two functions f and g. Then our set X with this distance function d makes a metric space. So this is the induced metric from the norm we have just defined above here. Now let me just sketch the proof of what? This line over here. Well, if you want too much details about this, then it takes about 2-3 class periods here, I believe. So then I don't want to spend too much time on this because we have only one class per week. So, but if you need some detailed proof of this line, then please let me know. Then I will make. You can take a photocopy of that for you. And then, but let me just make a sketch for its proof here, roughly. The proofs of the first two conditions are very much straightforward and easy, but the proof of the third condition here is very much time consuming. How do you check out the first condition there? Of course, if we have the identically zero function, if you have a identically zero function, have an identically zero function, what happens to its norm? Then its norm is this, because our function f is identically zero, so its norm must be this, which is the zero integration of the zero function, identically zero function, which must be zero, trivially. So if you have a zero function, identically zero function, its norm value is zero as well. If you have an identically zero function, then its norm value is zero as well. So we claimed the backward direction of this first condition. How do we, justify the forward direction of that first condition? If norm of f is equal to 0, then we want to claim the function f must be identically 0 as well. Then how do we claim this line? Using, again, the contradiction we have already experienced on the very first example today, when p is equal to 1, right? Yeah. Using the contradiction. If f is not identically 0, then again, there exists some point x not on the whole real number line R, at which absolute value of the function value is some positive number. Then it's time to use what? It's time to use the continuity of the function f at the point x naught we have chosen. The function f is continuous. At the point x naught we have chosen on the previous line, right? Yeah, there exists some positive number delta such that function values of f at any point x is more than half of epsilon for all x in the delta neighborhood around x naught. That's what that means. Yeah, again, that's what's happening. Here is the point x naught at which absolute value of function f, absolute value of f function value is positive. And then because absolute value of f is continuous, again what? There is some delta neighborhood around x naught at which all function values are what? More than half of epsilon line. That's what it is. That's true because f is continuous. So the continuity condition is very strong. Then what must be happened to the norm of the function f here, which is same as 1 over p's power of improper integration on the whole real number line, the p's power of the function f of x. Again, I don't care what will be happened outside of the delta neighborhood around x naught, but I just care what happens inside that delta neighborhood around x naught. Because in the inside of the delta neighborhood around x naught, function value, absolute value of f function value is more than half of epsilon. So this integration must be at least more than or equal to what? More than or equal to delta times what? Delta times half of epsilon to the power p to the power 1 over p. That must be happened at least. Yeah. Yeah, this function value is more than half of epsilon on that delta neighborhood. So this whole integrand function values must be at least what? P's power of half of epsilon on that delta neighborhood. But we have another power 1 over p outside. So this whole integration value must be at least that number, which is definitely positive. That's a contradiction. We have that contradiction because what? We supposed our function f is not identically 0. If the function f is not identically 0, then what? Its norm value is some positive number. That's a contradiction. So we combined, both of those, and then we claimed what? The equivalency of those two. Okay? Equivalency of those two. How about the second condition? That's very much straightforward by the integration property again, right? Norm of any constant multiple of the function f in the set is same as 1 over pth power of improper integration on the whole real number line, pth power of f of x. So the absolute value. I shouldn't forget, I shouldn't skip the absolute value sign. Yeah. So what? Absolute value of CF, pth power of absolute value of CF function. And that's same as and then by the integration property, we can take that constant out. And if you take that constant outside of integration, then 1 over pth power is waiting for that. So pth power of absolute value of c to the power 1 over p. So what? Then must be just the absolute value of the constant c times. What's left over then? The leftover is 1 over pth power of integration of pth power of the function f. That's the only thing left over inside. Then that's same as absolute value of the constant c times this integration, which is what? The norm of the function f. So we could easily check norm of constant multiple is same as the constant multiple of the norm, which is exactly the second condition to be a normed space. Well, let me introduce, let me see. Two different lemmas to check the third condition of the normed space for this example here. So as I have mentioned, it may take 2 or 3 class periods to check only this third condition to be a normed space for our example, for our set to be a normed space. So then I will just introduce the lemmas, the tools we must use to check the third condition. And then if you are interested in that, then you can make a photocopy of my class note here. Yeah. So the third condition we must check is the following. The norm of the addition of two functions f and g in this set is less than or equal to addition of separate norms for all f and g in the set x there. And that's what we must check, which is called the Minkowski's inequality. That's the name of this inequality. That's so-called, do I have the right spelling? Yes, Minkowski. M-I-N-K-O-W-S-K-Y. K-O-W-S-K-Y. Minkowski's inequality. To prove this Minkowski's inequality, we need two different lemmas which are called Young's inequalities and Holder's inequalities. Yeah, we need two different inequality lemmas to prove this Minkowski's inequality for the third condition to be a normed space of this set X. Then let me just introduce the two different inequality lemmas here. And the first lemma we need is so-called Young's inequality. Young's inequality. Which says, if you have two different numbers P and Q, both of which are more than 1, such that the sum of their reciprocals is precisely 1. For example, you can choose +2 and +2 for both, for example. And then what happens to the sum of their reciprocals? That must be positive half, and the sum of +1/2 and another +1/2, which must be precisely 1. So, yeah, that's one of the examples, pairs for P and Q we may choose. But by the way, if you choose two finite numbers which are more than 1 and their sum of reciprocals is +1 precisely, and A and B are two different non-negative numbers, then we will have the following Young's inequality, which is the following. Product of the two numbers A and B here is less than or equal to sum of the ratio of pth power of the first number A divided by P and the ratio of qth power of the second number B divided by Q. Yeah, this inequality is called the Young's inequality. Yeah, we have two finite numbers which are more than or equal to 1, satisfying this equation here. Their sum of reciprocals must be precisely +1. For example, 2 and 2 on both, that will work. And then, if you have any two non-negative real numbers, then this is how we estimate the product of those two real numbers A and B. The product of the two numbers A and B must be less than or equal to this sum over here. Sum of the ratio of pth power of the first number A and the number P and what? Another ratio of qth power of the second number B and the number Q itself. This is so-called Young's inequality, which will be needed to prove this Minkowski's inequality. I hope I have a minute to introduce the second inequality lemma, which is called Holder's inequality. And let me erase this line definition. Another lemma we need to prove the Minkowski's inequality is called Holder's inequality. Umlaut notation is above O there. Holder's inequality. Again, if P and Q are finite numbers which are more than or equal to 1, such that sum of their reciprocals is positive 1 precisely. And if the first function f is p's power integrable, and the second function g is q's power integrable. So what I mean is, the p's power of the first function f is integrable, and q's power of the second function g is also integrable. Then the result of that Holder's inequality says the product of f and g, the product of the two functions f and g, is also integrable. If the first function f is p's power integrable, and the second function g is q's power integrable, and then the result of that Holder's inequality says what? The product of the two functions f and g is just integrable. And one more inequality result, which is called Holder's inequality. Integration of the product of two functions f and g is less than or equal to, less than or equal to norm of the first function f in LP. You understand what LP norm is, right? What I mean is, let me rewrite it. That may get you some confusion. That's less than or equal to 1 over p's power of integration of p's power of the first function f times 1 over q's power of integration of the q's power of the second function g. We have this inequality here. This is so-called Holder's inequality. Holder's inequality we will need to prove the Minkowski's inequality. So to prove the Minkowski's inequality here, which is the third condition to be a normed space of this set, we must use both inequality lemmas, Young's inequality here and the Holder's inequality there. And it takes very much time consuming to finish out the proof of that Minkowski's inequality. So I believe some of you may be interested in its proof, and if you are interested in, please, you can take a photocopy of its proof here. So I believe that's enough for today.